All right, Code Warriors, welcome back to AI.Code.Cast. Today, we're diving deep into a classic algorithmic challenge.
Yep.
One that really pops up in those technical interviews.
Absolutely a favorite.
The longest increasing path in a matrix.
Yeah, that's right.
It's a real brain teaser.
It is. It's a good one.
Tests those problem-solving skills.
For sure.
And your ability to think algorithmically.
Mm-hmm.
So imagine you're facing this problem in an interview.
Okay.
You're presented with a grid of numbers, like a spreadsheet.
Right.
But instead of formulas,
Okay.
you're thinking about paths.
All right. I like it.
The challenge is to find the longest sequence of numbers in this grid,
Okay.
where each number is strictly larger than the one before it.
Got it.
And you can only move up, down, left, or right.
Okay.
No diagonals allowed.
Interesting. Like navigating a maze, but you can only go to higher ground.
Exactly.
Yeah.
And, of course, the interviewer wants the absolute longest path,
Of course they do.
not just any increasing path.
Right.
Where would you even begin to tackle this?
Well, the first thing that comes to mind is just trying every single path brute force,
Okay.
starting from each cell in the matrix.
So, like a relentless explorer, we try every route, hoping to stumble upon the longest one.
Yeah. Basically.
Sounds exhausting, though. Is that really the best way?
It's definitely a starting point,
Okay.
but as you said, it could get really, really computationally expensive.
Especially for larger grids.
Especially for larger grids, yeah.
Okay.
This approach, basically what it is depth-first search, or DFS,
Okay.
to systematically traverse the grid.
So DFS helps us systematically cover all the possibilities. But
Exactly.
wouldn't that take forever if the grid is massive?
Yeah. And that's the issue with this brute force DFS approach.
Oh.
It has what we call exponential time complexity,
Oh.
meaning as the grid grows,
Okay.
the time it takes to solve it just explodes.
So you're likely to hit that dreaded time limit,
Yeah.
exceeded error.
Yeah, exactly. In an
Well-
interview setting, that's not what you want.
Ouch, that's not the impression you want to make.
No, it's not.
So how do we escape this brute force trap
Right.
and find a more efficient solution? Any hints?
Think about it this way.
Yeah.
If you're exploring a maze, how can you avoid doing the same work twice?
Okay.
Like, what if you started leaving breadcrumbs?
Ah, so it's like remembering what we've already explored and using that knowledge to our advantage. Is that where memoization comes in?
Yeah, that's exactly it.
Okay. I'm starting to see how that could help us speed things up,
Yeah.
but how does it apply to this longest increasing path problem?
So remember, with brute force DFS,
Okay.
we might be calculating the longest path from a given cell multiple times, but with memoization,
Okay.
we can store the result of that calculation
Gotcha.
in a table.
So if we ever see that cell again, we just look up the answer.
Exactly.
You got it.
That makes a lot of sense. We're basically trading space for time,
Yeah.
using some extra memory, but saving a ton of computation.
That's the trade-off. Yeah.
And in this case, in most cases, the time savings is worth it.
So Memoized DFS seems like a promising approach.
It is.
Can we break it down a bit further? Like, what would the steps involved look like?
Yeah, so first we'd create our memoization table. It
Okay.
would be a 2D array,
Okay.
the same size as our matrix.
Got it.
And we'd initialize it with like medicine 1 or something to say we haven't visited it yet.
So our memoization table is like a blank slate ready to store our discoveries.
Exactly.
What's next?
Then we define a function. Let's call it DFS.
Okay.
It'll take in the row and column of the cell.
Got it. So DFS is our explorer function starting at a specific cell.
Right.
What happens inside?
First, we got to handle the base cases.
Okay.
Like if the row or column are out of bounds.
Right, when we hit the edge of the matrix.
Exactly. Then we just return 0.
Makes sense.
Similarly, if we try to move to a cell with a smaller or equal value.
Like our explorer hitting a wall.
Yeah, exactly. We return 0.
Okay.
Now, here's the memoization part.
Yeah, the magic.
Before we do anything else, we check our table.
Gotcha.
If the entry for this cell is not Nevis 1.
Meaning we've already been here.
Exactly. Then we just return that value.
We avoid the extra work.
Exactly.
But what if it is natus 1?
Then we got to explore.
Okay.
We call DFs in all 4 neighbors.
Up, down, left, right?
Yep. But only if the move is valid.
Meaning in bounds and larger value.
Right. And then we take the maximum of all those.
Okay, so we're recursively exploring each valid path and keeping track of the longest one.
You got it.
What do we do with that maximum?
We add 1 to include the current cell.
Okay,
And that's what we store in the table.
brilliant. So we're remembering what we find, but how do we start? Do we call DFs for the first cell?
Not quite.
Okay,
We want the longest path in the whole matrix.
right, not just from one starting point.
So we have to call DFs for every cell.
And keep track of the overall maximum. Like
Exactly.
we're sending explorers out from every cell, and the one that finds the longest path wins.
I like that analogy. Yeah.
This Memoized DFS is starting to feel pretty powerful,
It is.
but I'm curious about its efficiency.
Hmm.
What's the time complexity?
So it's OM times N, where M and N are the dimensions of the matrix,
Okay.
because we only compute the longest path for each cell once.
So we tamed that exponential monster,
We did, yeah.
achieved a much more manageable time complexity.
Much better.
That's a big win.
It is.
This Memoized DFS seems pretty solid, but are there any other approaches, maybe something completely different?
There's one called peeling the onion
Okay.
that uses topological sorting.
Peeling the onion. Now you've got me curious.
It's a fun one. We'll talk about it after the break.
That sounds good.
Welcome back to AI.Code.Cast. Before the break, we were talking about peeling the onion.
Yes, you mentioned it uses something called topological sorting.
Right.
To be honest, that sounds kind of intimidating. Can you break that down?
Yeah, absolutely.
Okay.
So remember how we're treating this matrix like a graph?
Okay, yeah.
In this approach, we actually build that graph. So each cell becomes a node,
Okay.
and we draw an edge between two nodes only if the value in the second one is bigger.
Okay, so we're visually representing those increasing values with the graph.
Exactly.
Okay. How does that help us find the longest path, though?
So the key here is because we're only moving to larger values.
Okay.
This graph has a special property. It's called a directed acyclic graph, or a DAG.
Okay. A DAG, no cycles.
Meaning you can't loop back around in the graph.
You can't keep going in circles.
Right, and that's super important for topological sorting.
No cycles, got it.
Yeah.
But I'm still a bit fuzzy on how this topological sorting thing actually works.
Okay, so imagine you have a bunch of tasks
Okay.
that depend on each other.
Right.
Some tasks you need to finish other ones first.
Right. Prerequisites.
Exactly, and topological sort is figuring out the right order to do them.
So in our matrix, the tasks are the cells,
Yeah,
and the dependencies are
Yeah.
the increasing values.
you got it. We need to process the cells in the right order to get the longest path.
So topological sort helps us line them up in a way that makes sense.
Exactly. All the edges go from left to right.
How do we actually do it, though? Are there algorithms for that?
Yeah, there are a few. One that's commonly used is Kahn's algorithm.
Okay.
It starts by finding all the source nodes,
The source nodes.
the ones with no incoming edges.
So in our matrix, those would be the cells with no smaller neighbors.
Exactly. They're at the bottom of our chain.
Okay.
When we put all those in a queue,
Or a queue.
then we go through that queue one by one.
Okay.
For each node, we remove it from the graph,
Okay.
and then we decrease what's called the in degree of all its neighbors.
Hold on. In degree.
Yeah, it's just how many edges point to a node.
Okay, so like the number of arrows pointing to it.
Right, so when we remove a node,
Yeah.
its neighbors have one fewer arrow pointing at them.
Okay. I see. We're keeping track of how many incoming edges each cell has.
Exactly.
What happens when a node's in degree hits 0?
That means it's ready to be processed.
Okay.
All its predecessors have been taken care of, so we
Okay.
add it to the queue.
And we keep repeating this.
Yeah, until the queue is empty.
So it's like we're peeling away layers of the graph,
That's where the name comes from.
starting with those that have no dependencies and working our way up.
Yeah, and as we do this, we also keep track of the longest path lengths.
Okay. How do we do that? Another table?
Yep, we create a distance array.
Okay.
Each entry corresponds to a node.
Got it.
Initially, for the source nodes, the distance is just 1.
Because the longest path is just the node itself.
What about the other nodes, though?
Yeah. How do we figure out their distances?
So as we process each node,
Okay.
we look at its neighbors.
Got it.
And for each neighbor, we check if the current node's path length plus 1 is bigger than the neighbor's current distance.
So we're updating the distances as we go.
Right, propagating that information through the layers.
What happens when we've processed all the nodes?
Then the largest value in the distance array is the length of the longest increasing path.
Wow, this peeling the onion is pretty neat.
It is. It's a cool way to solve it.
Seems like we're unraveling the longest path very systematically.
Yeah, topological sort helps us do that.
Okay, before we get too carried away, let's recap the steps.
Sure.
First, we build our graph from the matrix edges, represent increasing values.
Right.
Then we find our source nodes, the ones with no incoming edges.
Yep.
We do our topological sorting Kahn's algorithm or something similar.
To get them in the right order.
Then we calculate those distances, the longest path lengths, starting with the source nodes.
And propagating that information.
And the biggest value in our distance array at the end is our answer.
Perfect. That's peeling the onion.
This is cool.
Yeah.
But how does it compare to the Memoized DFS?
good question.
Are they equally efficient, or does one have an edge?
So they both have the same time complexity.
Okay.
OM times N.
All right, so both pretty efficient.
Yeah, it often comes down to personal preference.
But different ways of thinking about it.
Exactly.
Memoized DFS might be more intuitive if you like recursion,
Yeah.
but peeling the onion is more visual and structured with the topological sorting.
Right. Different tools for different jobs.
This is fascinating. We've seen two really different ways to solve the same problem.
It shows how creative you can be with algorithms.
Yeah, and how versatile they can be.
Hmm.
Now, what if we change the rules a bit? What if you could only move diagonally?
Ooh, that's interesting.
How would that change our approach?
I think we can still use our methods,
Okay,
but we'll need to adapt them.
let's see how after the break. Welcome back to AI.Code.Cast. Before the break, we were about to dive into that diagonal movement twist.
Yeah, how would our algorithms handle that?
Exactly. So let's start with our Memoized DFS.
Okay.
Do you think it can even handle that diagonal constraint?
Well, the whole idea of memoization is to avoid those redundant calculations, and that doesn't change just because we're moving diagonally.
So I think the core logic should still be good.
Yeah, the core logic should hold up.
But we'll have to adjust how we explore within that DSS function.
Exactly. Instead of checking those 4 neighbors up, down, left, right,
Yeah.
we now got to consider the 4 diagonal ones.
Top left, top right, bottom left,
Yeah,
bottom right.
Yeah, you got it.
So we're basically just changing what it means to be a neighbor.
Exactly.
But the rest of the logic, like checking for out of bounds and using the memoization table, that all stays the same.
Yeah, all that stays the same.
That's the beauty of memoization. It's adaptability.
Exactly.
You just change how we traverse the matrix.
Right.
The underlying principle of storing and reusing results, that's what stays the same. Okay, that seems like a pretty straightforward tweak for Memoized DFS.
Yeah.
But what about peeling the onion? How does diagonal movement affect our graph?
So remember how we build the graph?
Yeah, connecting cells with edges.
Well, now instead of connecting to horizontal and vertical neighbors,
Okay.
we connect them to their diagonal neighbors that have larger values.
So the edges represent those diagonal relationships now.
Exactly.
But once we have that diagonal graph,
Yeah,
the rest of the topological sorting stays the same.
you got it. Kahn's algorithm, all of that still works.
We're just working with a different graph structure.
Right, a structure that reflects those new diagonal movements.
This is really cool. It shows how understanding those core principles
Yeah,
lets us adapt to all these variations.
absolutely.
It's not about memorizing steps.
No.
It's about those underlying concepts.
That's what makes a good problem solver.
It's about recognizing those patterns and applying those fundamental techniques.
And being able to adapt them.
This has been an awesome deep dive into algorithm.
I agree.
We tackled that longest increasing path problem.
We did.
Explored memoized DFS, peeling the onion,
All sorts of fun stuff.
even adapted them for diagonal movements.
Did a good one.
I hope all you listeners out there feel ready to tackle some of your own algorithmic challenges now.
Yeah.
Remember, practice makes perfect.
It really does.
The more you play with these techniques,
The better you'll get.
the more intuitive they become.
Absolutely.
That's all for today's AI.Code.Cast.
See you next time.
Until then, keep coding, keep exploring, and never stop learning.